morning, everybody. Buongiorno a tutte e tutti. So I will make this topic regarding the semi-dynamic metal sealing. So I will explain the base theory of what we call the semi-dynamic metal sealing, and also we will see two examples of valve application, one on more dedicated on fugitive emission, and the other one on a shut-off sealing application for triple offset butterfly valve. Briefly to present myself. So I've been working in Technetics Group for 16 years, so I'm a mechanical engineer. I made 12 years in charge of special engineering project, every unusual project, and now I'm engineering manager for 4 years, and I share my time between the management and also the development of specific projects, quite a lot in the area of the dynamic sealing. So the agenda of this presentation. First of all, I will remind you what is the common use of the metal seals in the industry, or what is the current state of the art, I could say. After, I will talk about what is the semi-dynamic sealing application. I will just remind you a definition, what is our definition by Technetics of semi-dynamic sealing. And some specificities, I will explain some specificities on the assembly design when we have some semi-dynamic sealing. And after, I will present two examples. The first example will be a quarter-turn metal stem sealing to replace a stuffing box. And the second example will be a shut-off sealing for triple offset butterfly valve. And you will see we are going to use two slightly different technologies for the two applications. Okay. And perhaps I will not talk about hydrogen. So let's start about the design philosophy, about what is a metal seal, how does it work. So here in this case, so I took the example of spring-energized metal seal, which is called by us Helicoflex, and I think there are some other names by competitors. So the idea it is to have a spring inside, an intermediate layer, and a sealing layer, which is usually soft. As you can see on the drawing, which is on the bottom of the slide, the idea is that you are going to compress. The spring is going to push on the intermediate layer, on the sealing layer, and the sealing layer is really going to penetrate the roughness of the flanges. So when you use some metal seals for static application, because in this case we are in case of static applications, very commonly sometimes the manufacturer is going to tell you, don't make us some flanges with a too low roughness. Sometimes we need some roughness to have the penetration and to make the leak path a little bit more complex. Okay. So the helium tightness, as my colleague was telling, is quite easily reachable with static metal seal because we don't have porosity. So after there is the contact with the flanges to deal with, but the porosity is not a problem. This technology is quite old because the first patent is dated 1969. So there is a big knowledge. We know the physical behavior, the design have been optimized, performance, also some lifetime regarding the creeping and so on are very well known. And also there are a lot of application specificities which are very well known. And the preconceived ideas, that's the last point, this concept seems to be very limited to the static sealing. That is explained on there is a small drawing on the bottom on the right. As I explained, there is a penetration of the sealing layer into the roughness. So we can say at one moment, if there is one movement of the flange, of course, as everything, there is an intimacy, we are going to scratch everything and we are going to lose the performance of the seal. Okay, that means normally if there is a movement, so this type of seal is normally not very suitable for the application where you have a movement of the flange. Okay, so it is, this is this idea, and this is what we have to deal with because there are now some needs to use also the metal seals for sometimes for some application where you have some movements, some motions of the flanges. So let's talk what is called a semi-dynamic now. So the dynamic sealing, when you call it about dynamic sealing, that means there is the motion of two contact surfaces between there. Typically, if you work with the pump, this is a mechanical seal where you have two flat faces, and there is a motion between the faces. The semi-dynamic sealing is also dynamic sealing, but with certain specificities. Normally, we consider that the motion first is very slow. Okay, that means that's a very slow movement. Probably at this speed, like I show with my hands, it would be probably the maximal speed we can figure out. The motion is not continuous. For example, it's an opening, closing, and after it stops. It's not a continuous motion. And generally speaking, what I tell is that the energy which is provided by the friction of the seal is negligible. That means, for example, for a mechanical seal, you have a power loss, and sometimes you need to cool down and so on. For a semi-dynamic sealing, normally this energy has not to be considered in the design of the system. Okay. And also, another definition for semi-dynamic sealing, it is also used in the jargon of the sealing for some static sealing, but which are submitted to regular cycle of compression and decompression with loss of contact. Typically, when you shut off a valve, you are going to close the seal, and you open, you close, and you repeat the compression of the seal a certain number of times. So the two examples I illustrated, typically the first example, it is a stuffing box. Okay, the stuffing box, there is a slow motion of a shaft or of a stem. And the lamellar seal, for example, is the application of the second definition of the semi-dynamic sealing. So the example of metal seal that you have for semi-dynamic applications is a very high temperature valve, or also the cryogenic sometimes. Cryogenic can be dealt also with polymer seal, but sometimes you have some requirement about the resistance to fire test. So the polymer seal are not suitable, so you need to deal with a metal seal. So the usual approach is with soft seal, with elastomer, also with plastomer. There is what I call live adaptation of the seal to the surface. That means what I designed on the top, on the right, that's a static contact profile. It's of course it's only to figure out what's happening. That means you have the roughness of the flanges, and the soft seal is going to adapt itself to the roughness of the flange. And when you are going to move, very simply, the soft seal is going to deform, and after it's going to reform itself at its new position. Okay, so the static contact profile can be always applied with a soft seal. With a metal seal, of course, it doesn't work. If you have made a first deformation at one place, once you move from place, of course, the roughness profile is not the same, so you are not going to repenetrate the surface. So we have two alternatives to work with the metal seal. The first one is very inspired from what is happening on the rotating mechanical seal. We work on the quality of the surface. So we have two polished surfaces with a quite hard high hardness, and the quality of the both surfaces will be the key of the performance. That's what is illustrated in the picture number 1. You can see it's very soft, and only the small gaps in the middle, these are the remaining gap which remain for the leak. The other possibility is a little bit more tricky. That means we have a soft seal coming in contact with harder flange, also with low roughness. But also, we can say that there will be a sort of migration of the soft material into the hard material. And finally, you will have a sort of motion soft versus soft, typically with a silver coating or with gold coating. At one moment, so the first motion, you don't have the sealing performance is not the best. But after 2 or 3 motions, there has been a migration, and finally you slide silver versus silver or gold versus gold, for example. What I call the buttering, so I put the picture with the butter on the bread, because it's exactly what's happening. You have the migration of the butter into the holes of the bread. That's what's kind of happening also in this case. So what are the expectable performance that we can reach? If we have a look to the first mechanism, which is hard versus hard, so the quality of the roughness is crucial for the performance. It is something well known, by the way, by the valve manufacturer. For example, for the triple offset butterfly valve, when you are working with massive metal seal, it's typically what you do. You don't have any spring back, but you are really going to play with the quality of the seal and of the counterface. The performance, of course, is limited because there is no gap filling of the interface. You have still this small hole which remain. However, the experience is showing that a bubble tightness remains achievable with such type of interface. Also, you can have some self-flapping. That means after the surface are going to slide between each other. And after one moment, there is a sort of self-flapping which occurs. The main advantage it is the durability of the cycle, because it's hard versus hard. So regarding the wear, of course, you can make a lot of operations. And the main application for that is typically the opening, closing, or the valve shut-off sealing. The second profile is very interesting also, more difficult to master, by the way. But we can really have some helium tightness because there is really a gap filling of the surface which doesn't occur with the first one. The performance, however, is limited in case of loss of contact because we have a soft material. So at one moment, that means if you repeat a compression, you can have some shearing constraints on the material and you can destroy a little bit the external layer, which is soft. Okay. So the shorter lifetime also because the flowing of the buttering, which is going to happen cycle after cycles. But typically, this type of mechanism can be used where you don't have any loss of contact when you have a sealing track. For example, you have one slide which is running always at the same place. Okay, you don't open, you don't close. But so at one moment you are going to butter a little bit always the same surface. So in this case, you can use this type of arrangement, which is very interesting in terms of performance, as you will see in the example in the next slide. So typically, the quarter-turn stem sealing can be done, it can be used, and also some linear stem sealing to replace some bellows also, for example. You replace a bellow by a translating seal with a very, very, very clean surface. It is something that with common industrial means is quite not so difficult to achieve, actually. So let's come to the example. Just, I don't know where I am. Okay, 11 minutes. So the first application was an application not for fugitive, developed not for fugitive emission initially, but it was developed for sealing a specific valve for a sodium application. Okay. So that was an application in which the graphite was not allowed because the liquid sodium is not can attack the graphite, so it was not possible to add a stuffing box. So for development, we developed this concept. So to simplify a little bit the reading, what you have to consider is that what is in the pink nuance is something which is rotating, and what is gray is static. And in the middle, you can see something which is yellow, and yellow it is a seal with a double torus. So we made actually an axial sealing with a spring energized ice seal. That means the external torus of the seal. I think there is a laser. Perhaps. Yes. So the external torus of the seal is going to slide here. So it is compressed by all this assembly, and it is going to slide on an external surface, which is here. That means there is really a movement of this soft seal on a counterface, which is with a very low roughness. So typically we have a roughness which is typical for the mechanical seals, so RA at 0.2 or 0.3 micrometer, so something like a mirror actually in this case. So you slide on the polished surface. Of course, there are some little bit of relief on the surface. So there is a spring inside the seal which is going to balance a little bit all the uncertainty of the surface. And so the initial purpose really to perform high performance sealing under 10 bars, so the pressure was not very high, and only 100 actuations, because this valve was dedicated normally to close an installation in case of emergency. So it is a valve which doesn't operate a lot normally. Okay. So to be honest, the results were very surprising for us because we were expecting something at 10-5, 10-4 millibar liter per second, and the results were beyond our expectation actually. So it was really impressive. So just to have a zoom on the application, you can see always the rotor part, which are the rotating parts. There is a system that I won't detail with the ball, which enables to compress the external torus, which was a little bit the key issue in terms of mechanic. So it was relatively small mock-up at 16 millimeter for the shaft diameter. Okay. So you can see there is the contact slide midpoint between the external torus and the lap sealing counterface is quite well identified, as you can see here at that point. Okay, so here we are static, and here we are dynamic at this point. So the seal is going to make a sort of travel, a quarter turn like this and like this. So the test results. So you can see, what you can see, the curve which is here in blue, it is the curve of the pressure, which has 10 bars. And the leak rate, you can see it is the red curve. So as you can see, that make quite, the curve make things to a sort of noise. You can see here, a lot of peak that goes up and down. That is each time we have an operation. That means, of course, when we are stabilized, we had a leak rate at 10 minus 10, 10 minus 10, 10 minus 9 millibar liter per second. And when we were moving, suddenly there was sort of, probably there was a sort of effect of buffering between the seal and the surface. And when we are moving, there is sort of, this buffer is going outside. So that makes a small peak, and after we come back. So each peak, it is one operation. So the buttering I was talking about was in this case quite moderate because the roughness of the counterface was low. But as you can see, we had a very nice sealing track on the gold-plated seal, which is here. Yeah. Okay. So these tests were made in our lab in Pierre Labs that we have in collaboration with Commissariat à l'Énergie Atomique in France. Okay. So, just by the way, so very impressive results. For your information, it's not written here. It's written that we went until 50 bars with the performance at 10 minus 7. That's true that the limitation of this concept is that after 200 operations, we observed that nevertheless we had some wear of the surface. So, as I was telling at the beginning, we are always sliding at the same place. Okay, so there was not opening and closing on the valve. We are always sliding at the same place, but however, with the time there is some friction and we started to lose performance. Okay. But for some application, typically with high temperature, it can be very useful. For example, for sealing some valve for molten salts. It's a new application at 600 degrees. Sometimes the molten salt also, like lysosomes, can attack the graphite. But very usually you have a very aggressive media. You have high temperature, but usually the pressure is low. So with the molten salt, when you reach 25 bars, it's already high, in fact. So the second example, is not less dedicated to fugitive emission. It's a spring-energized metal seal design for a triple offset butterfly valve. So here in this case, so we have in a case a little bit different. So we don't have the motion is not continuous. So we are going to open and close the valve. So here the goal it is really to have something which is going to be repeatable, and we have to conserve the performance over the time, operations after operation. So there was a know-how, first of all, on this application. So the double offset butterfly valve have been sealed with metal seal for quite a long time now. It's especially well known, for example, for cryogenic application for the liquid gas. So it's old oil and gas application, for which this type of technology can be used. So with a quite good resistance over the time. So we wanted to expand this concept to the triple offset butterfly valve, because the triple offset butterfly valve is more standard now in the industry. And also we wanted to improve the performance. So the common performance with this seal was a class B according ISO 52008. And the goal was to reach a class A ISO 5208. So actually that is a zero bubble tightness on the valve. So we had to work a little bit also on the coating So the concept which was developed, it's a patented concept. So that's a sort of radial seal, which is integrated in a special custom design box. So you can see the seal here at that point. Well, you can see the box. And I say it is radial because it is going to seal on the external side and on the internal side. So it's not really radial because it's an elliptic shape, actually, but let's say it's radial. So there is the beige part, which is the box going to maintain the seal, and which is going to act as a limiter in the movement of the butterfly, because it is normally what is expected for a seal for triple offset butterfly valve, according to the standard. The elliptic surface, which are designed into the box, enable to have a uniform compression all around the circumference. Otherwise, we should have to make an elliptic seal. So the seal is made elliptic by the box itself. So the performance were quite interesting. So we made some different design with Helicoflex seal, which is our brand name for the spring energized metal seal. We had also different sealing layers to optimize the wear behavior. These tests were made on a Pentair valve that we purchased and that we readapt with. We made an own design on seal for PN100. And we have one current design which is seal made of Inconel 600 plus wear treatment. Bon, why Inconel 600? Because it's a quite convenient material for everybody. The temperature resistance is high. The corrosion resistance is also interesting. It can be used for the NACE application, for seawater and so on. So it's quite, I would say, a whole path vehicles for for the metal seal. So we made our test in helium, even we were not looking for very high helium leak rate in this case, but we are used to work with helium. And as you can see, the performance at 11 bar, even after 750 cycles, were very good. So we are class A until 300 cycles, and after we are class AA, which is a class just below, after 750 cycles. But I would say it was a very good class A, aka because the criteria was 45 cubic millimeter per second, and we were between 3 and 11. So it was definitely very good. Just one comment: you have to consider also that this design was made on a valve for which we didn't have the drawing. So we made a reverse engineering of the valve. To make a reverse engineering on triple offset butterfly valve is not very easy because the geometry is very specific. And we adapt the design, and despite this point, we managed to have a very good performance. Okay, so the best performance was observed with the hard polished seal. So it is something a little bit counterintuitive if you remember the first slide where I was talking about the soft material penetrating in the roughness and so on. So we didn't look we didn't try to make a better ring. To be honest, we tried at the beginning, but it didn't work because there was too many wear on the material. But we saw also with this configuration hard versus hard, we can reach the class A over a big amount of cycles. Okay. So before, the class A was targeted only with the soft polymer seals. So the idea is also to propose something a little bit different. Of course, these targets are achievable through a clever seal and seed combination, like I say quite often, and probably my colleague will say the same thing. The seal alone doesn't mean nothing, or in face of the seal you have a counter surface, and the sealing performance is a fruit of a collaboration between the seal manufacturer and the customer, of course. So the conclusion of this presentation to say that the semi-dynamic metal sealing solution is a key for the valve optimization, especially if you want to combine the performance and also the fire-safe requirements. It can be actual and for future extreme applications. We can use different contact mechanisms, so I presented you the two ones, and seal design according to the performance expectation. And of course, the best performance achievable also with a good surface engineering on both sides, on the seal and the counterface. And of course, like I was telling just before, a strong collaboration between the valve manufacturer and the seal supplier. Thank you for your attention.
Thank you, Laurent.
So if you have any question. So sorry, everybody talked about hydrogen, not me, but...
Yes, thank you for the presentation. My question is, you showed a lot of interesting performance at ambient temperature, but have you done the same testing for cryogenic? Because this type of valve will go for LNG market primarily?
So for cryogenic, we'll do a test with an OEM with which we are working on probably this year, okay, on a quite big dimension. It's for DN600. So we are currently the setting of the valve. It is in the hands of the OEM currently. We are quite optimistic, nevertheless, because as I was saying, the concept of the helicoflex used for the triple offset butterfly valve, there is a pass. We have a pass in the double offset butterfly valve, and we have an excellent return of experience on the double offset of butterfly valve on cryogenic application for the liquid methane. Typically, KSB, for example, KSB Amri in France is one of our big customers, and I think we deliver 1,000 seals. So normally, I'm not so worried about that. But it will be tested, yes, for sure.
Laurent, thank you for your presentation. It's great, thank you.
The torus seal, the metal torus seal, spring energized, it's like a C shape that you have, and it's facing towards, let's say the inner wall. The C is facing this way, rotated around. Could you make the same seal with the C shape pointing down and rotate that around with the spring underneath?
We could do that. To be honest, we tried. Alors, the issue after we chose effectively, we chose on the you talk about the first example. We chose to work actually for one single reason, is that the C shape is quite rigid. In fact, that means when you are actually at one moment the C shape, you don't have any axisymmetric rigidity. So that means when you are going to rotate, the C shape can do this thing. That means at one moment, if you have an irregularity, there is a spring, and after you can follow, especially because the motion is slow. The problem is that when you work radially, it's a little bit different, because of course each wire, each coil is going to act independently, but the problem is that the C itself has its own rigidity. Okay, you understand?
Yes.
So the problem is that this rigidity axisymmetrically is much higher, so it's a little bit more difficult. So at one moment, it's difficult to explain. Sorry, I work a lot. I talk a lot with my hands. I'm in Italy, that's normal. But that means that here at one moment, if you have one irregularity, you are going to act like this, and you will have one point. And the problem is the axisymmetric rigidity of layer will block you to envelope a little bit this point. You understand what I mean? So actually, you don't have the problem, but radially it's a little bit more complex. So radially, I would advise you to go to my colleague from Saint-Gobain, because but with the plastomer, you are much less this problem.
Because we manufacture a metal seal ourselves that we designed. We have a different wall thickness on the inner diameter than we do on the external portion
in this case,
of the C.
yes.
So we have a different wall thickness there, and that seems to work for us, but we're now working on spring energizing that shape because we have it energized with elastomer.
Yeah.
But we'd like to go to higher temperatures and lower temperatures than the elastomer allows.
That can be tested anywhere. So I think the idea to work with different wall thickness is very good, because that means you can have a high wall thickness on the external parts, for example, if you don't move. On the internal part, to reduce a little bit the axisymmetric stiffness, you can reduce the stiffness. We don't do that because we shape the seal from a sheet at the beginning, but that's the idea. And after, I always say that life is a compromise. So you must have the compromise to have something which is soft enough to reduce the axisymmetric stiffness, and also thick enough after for the function to withstand the pressure, for example, and things like this.
Yes, we're just staying out of the plastic deformation range. We're staying in the elastic deformation range by doing that, by changing the wall thicknesses from the inside to the outside. So it's a secret.
Yeah,
right. How thick you make the inside versus the outside. It's a ratio.
But I think from my point of view, being plastic on the inside side is probably the good idea, because you can have also the elasticity given by the spring, and having something very plastic in the middle, which is pushed by the spring. What's happened on the polymer seal? On the polymer seal, you are going not to use actually the elasticity of the spring, and perhaps a little bit less the elasticity of the polymer. Tell me if I say something wrong. I'm not specialist, but that's my physical interpretation.
Yeah, the interest would be in the springs, so we could pass cryogenic and fire testing.
Yeah.
Okay, thank you.
You're welcome.
Okay, seems to be okay.
Emmanuel.
Last question.
Thank you for your presentation. Two points. The first one, could we consider, considering your experience when you perform a thermal cycle, small motion due to dilatation, is it a problem? It can be a problem, or there is an accommodation?
Not really, because as I was telling Emmanuel, we are talking about slow motion. So the slow motion can be due to different factors, and the thermal expansion is typically one of these factors. By the way, it is something which is well known after by the experience of our company on the static application, where we have, for example, a compromise which is between the typical roughness of RA 1.6 micrometer for static sealing, and the RA 0.2 or 0.3 for the semi-dynamic. And sometimes we make some design with the RA 0.4 or 0.8, which that we advise to our customers, with some silver coating, and that works quite well for the micro motion, which can be due to the thermal expansion typically. So after also, thermal expansion is a little bit at the limit because, well, of course, if we talk about thermal expansion on a shaft of 2 meter long, of course, we are talking about expansion of in millimeter. In this case, it's semi-dynamic. After, on the small application, we have expansion of about tenths of millimeter. So in this case, it can be nearly considered as a static application. Actually, it is treated a little bit that way.
Okay, thank you. And the second one, you show the measurement of leak rate.
Yeah.
And we saw some peaks before the pressure. Could you explain?
Yes. I don't remember.
As I remember, the curve of the pressure is blue, and the leak rate was red.
I don't remember.
You don't remember?
I should have a look to the curve.
Okay.
Sorry. It's okay. Sorry. Okay, we are. So I think it was further. Which one? Yeah, the pressure was blue, and at the beginning there was a peak. So I was probably so we were under vacuum in this case, so there was no pressure. And I think it were typically the first operations. So the first operation, so we were already good, but probably we had a little more leakage. The time for the track to be stabilized, and that's probably the reason why. Okay.
Okay, no more question. Next presentation from Mr.
Okay.
Loïc Deneville, Total Energies.
Thank you very much.
Thank
Grazie
you.
mille.
Thank you, Laurent.